everyone, ready for a super fast crash course on one of the most fundamental topics in science? Today, we're diving into chemical reactions and equations. Whether you're cramming for a test or you're just curious, let's get right to it. So here's the game plan. We're going to hit 5 key topics. First, spotting change in the world around us. Then, we'll learn the secret language of reactions. After that, the all-important balancing act. Then, we'll meet the different families of reactions. And finally, we'll talk about energy and how to control a reaction's speed. Let's go! So let me ask you something. When you leave milk out and it turns into yogurt, what's going on there? Is it magic? Or is it something a little more, scientific? Well, spoiler alert, it's all chemistry. And it all boils down to this one crucial difference: physical versus chemical change. Look, a physical change is just a change in appearance. Water freezing to ice, it's still H2O, right? But a chemical change, like iron turning to rust, now that's different. You've created a totally new substance with brand new properties. That's where things get interesting. Okay, first up, a world of change. We're going to learn how to become chemical detectives and spot these transformations happening all around us. So what is a chemical reaction, really? Well, at its heart, it's just a big reshuffling of atoms. Think of it like Legos. You break apart the bonds holding one creation together, and you use those same bricks to build something completely new. Old bonds break, new bonds form, and poof, you've got new stuff. So how do you know if a reaction has actually happened? You look for the clues. There are 5 big ones: a sudden change in color, a change in temperature, either getting hot or cold, a substance changing its state, like a liquid turning solid, bubbles of gas appearing out of nowhere, or a solid forming in a liquid, which we call a precipitate. All right, so now that we can spot a reaction, let's figure out how chemists actually write it all down. It's time to learn the language of reactions. Let's read the code. Every chemical equation is like a simple story or a recipe. On the left side of the arrow, you've got your starting ingredients. We call those the reactants. And on the right side, that's what you make at the end, the products. That's it, what you start with and what you end with. But chemists like to pack in more detail, so they use these little symbols. You'll see an S for solid, an L for liquid, and a G for gas. And this one, AQ, just means aqueous, which is a fancy way of saying it's dissolved in water. Oh, and if you ever see this little triangle symbol over the arrow, that's just a shortcut for we added heat. Okay, time for what might be the most important skill for a chemist to learn. Welcome to the balancing act, where everything has to be perfectly equal. And you might be asking, why? Why do we have to go through all this trouble to balance equations? Can't we just list what we started with and what we ended with and just be done with it? Well, the answer is one of the most fundamental rules of the entire universe, the law of conservation of mass. It basically says you can't just create matter out of thin air, and you can't make it disappear. So whatever atoms you start with, you absolutely must end with that exact same number of atoms. It's a non-negotiable rule. Okay, let's try one. Look at this equation. The key is to be systematic. First, just make a list of the atoms on both sides. Then, my tip is to start with the most complicated looking thing. In this case, we'll balance the oxygen first. That messes up our hydrogen count, so we fix that next. And last, we balance the lonely iron atom. And there you have it, the final balanced equation. It's like a puzzle, not guesswork. Fantastic! So we know how to write them, we know how to balance them. Now let's check out the common patterns they fall into. It's time to meet the family of reactions. You know, chemists love to categorize. And it turns out most reactions fit into one of 4 big families. You've got combination, where 2 things become one. The exact opposite is decomposition, where one thing breaks into 2 or more. Then there's single displacement, where one element boots another one out of a partnership. And finally, double displacement, where 2 couples just swap partners. If you can spot these patterns, you can predict what's going to happen. Now, speaking of decomposition, let's zoom in on that for a second, because this is pretty cool. There are 3 main ways you can force something to break apart. You can use heat, that's called thermal decomposition. You can use light, or photolytic decomposition, which is why silver chloride turns gray in the sun. Or you can use electricity, which is electrolytic decomposition. That's how we split water into hydrogen and oxygen. Hey, remember earlier when we said one of the signs of a reaction was a solid forming? Well, that solid has a name. It's called a precipitate. It's just an insoluble solid that kind of appears out of nowhere and falls to the bottom of the liquid. You see this happen a lot in those double displacement reactions. We're on the home stretch. Last section. Let's talk about energy and speed control, or what we can call reaction dynamics. When it comes to energy, every reaction does one of two things. It either releases energy or it absorbs it. If it releases heat, it's exothermic. Just think exo for exit. These feel hot, like the respiration happening in your body right now. If it absorbs heat, it's endothermic. Think endo for enter. These feel cold, like photosynthesis in a plant leaf. Okay, but what if you want to change how fast a reaction goes? Well, for that, sometimes you need, how to put this? You need the friend who starts a fight but isn't directly involved. It's a weird analogy, but it's the perfect way to think about our next concept. That friend is a catalyst. Here's the official definition. A catalyst is a substance that changes the speed of a reaction, either makes it faster or slower, but here's the crazy part. It doesn't get used up in the process. It just helps out and then walks away unchanged. Catalysts are the true puppet masters of the chemical world. So I guess the biggest thing to take away from all this is that chemistry isn't just something stuck in a textbook or a lab. It is happening literally everywhere all the time. So I'll leave you with this question to think about. What chemical reactions are happening around you and even inside you right this very second? From the battery in your phone to the food you're digesting, our world is just one giant, beautiful chemical reaction.